Yeah, so we saw that there are multiple ways of making halogen alkanes. We start with the alkanes. If we start with that, then we can add a halogen to them. And as long as there's ultraviolet light allowing them to homolytically break down, then you can get free radical substitution. The thing is that only one atom is replaced at a time, and that's how you get the halogen alkane. But there is a faster method, which is electrophilic addition, in which you start with an alkene, and that alkene undergoes EPA, and that's electrophilic addition or EA. And then it forms halogen alkane. The good idea or the good thing about this reaction is that there's no byproduct. So if you add things in the right quantity, then you don't really have to uh, do fractional distillation. If they are just right, then you will get a pure sample of halogen alkane, and that saves us a lot of time and energy. Which product you get depends on what you started with. So if you start with an acid with hydrogen and an halogen in it, then you will get a product that will be similar to the product that you might get through an alkane and substitution alkane. But if you start with a pure halogen or an aqueous halogen, then you might end up with different products. With pure halogen, we get two atoms of halogen added to the molecule. But if you start with water, then because OH minus is a stronger nucleophile than Br, what you get is that you might get an halogen alcohol. That OH comes in at one carbon instead of the bromine. So that's also possible. That instead of getting two chlorine or two bromine, you also get one bromine and one OH. If you start with alcohol, then there are again multiple ways of using an alcohol to do electro substitution, and nucleophilic substitution is one method through which you can get alcohols reacted with acids, and these acids will all obviously have uh, halogen in them. And if they do, then they will basically substitute OH with Cl or Br or something, and you'll get water as a byproduct. In the case of salt, we try to make sure that we add some acid to it so that the process kickstarts. And KBr or some other NaBr or NaCl will do the same process, except they will create a different byproduct. This byproduct can react with the acid and then produce salt and water again. There are three other ways which are specific to AS chemistry, and that is that you can start with PCl3, PCl5, or SOCl2, and they will react with alcohol and produce halogen alkane. Again, in all of them, OH goes out and the halogen comes in, and then something else might happen to the OH. For example, in the first one, each chlorine replaces one OH, and phosphorus ends up with OH. But then that OH, because of the way it's bonded, and phosphorus and oxygen and their relative electronegativities, they play a part, and you end up with phosphorus acid. This reaction requires a lot of heat, but you can use the same process but achieve similar results in presence of PCl5. This will save you energy because you won't need to heat it up. And so with PCl5, what happens is that OH is replaced with one chlorine. One chlorine reacts with hydrogen. Both of them are replaced with oxygen in the PCl5 compound. So you end up with POCl3, HCl, and the halogen alkane that you wanted to make. Of course, you can separate them out through fractional distillation. SOCl2 is the cleanest method because what it does is it basically replaces OH with Cl, and one H reacts with another Cl, and the oxygen reacts with S and O in making SO2. This is clean because you're ending up with two gaseous compounds. One is HCl, one is SO2, which will obviously evaporate, leaving behind the halogen alkane that you wanted. Another important idea to remember was that chlorine is the primary culprit when it comes to ozone gas depletion in the upper atmosphere. And the reason people used halogen alkanes initially, and they were so excited to use them, was because they seem to be very inert, especially in the situation that we have these days and room temperature and all that. But in the upper atmosphere, they start to actually react and they produce catastrophic effects, as we have seen. One process that we use to elongate carbon chain, again, that is a reaction of bromine or other halogen, Now we are on to what halogen alkanes are used for. So we are done with how you make halogen alkanes. We've seen six methods to that, but now we are moving on to how we can use halogen alkanes and what we can produce from them. So for example, one halogen alkane, what you can do is that because halogen in there is going to leave out as a negative ion or a nucleophile, then they can be substituted with a stronger nucleophile. Or in the right condition, it doesn't have to be even stronger. It can just replace them if the conditions are right. For example, in the case you have cyanide, cyanide is a nucleophile. It has a lone pair. An important thing to remember what cyanide is that the lone pair that actually attacks is the lone pair on carbon. It's not the lone pair on the nitrogen that attacks. It's mainly the carbon. So when it attacks, it forms organic compounds, and organic compounds are not called cyanides. They're called nitriles if they have the C triple bond N group. This C triple bond N has two further reactions, which I will go over now. And what they do is that you have propane nitrile formed, and what has happened is that you started with ethyl bromide or bromoethane, but now you're ending up with propane nitrile. So the primary key difference here is that you have basically created a chain of 3 carbons, starting with the compound with just 2 carbons. So this is a useful thing whenever you want to elongate the chain. And there is a chapter that will talk about organic synthesis, which is the last chapter of organic chemistry, where they bring everything together. And in in the organic synthesis, this really helps us out. Understanding that whenever you want to elongate a carbon chain, you should try to add nitrile in there. Of course, how you add nitrile? One way to do that is by first making a halogen alkane where you want, and then you can add the nitriles, the cyanide group in there. So wherever you want, you can just, so for example, we took this example that we started with OH and we wanted to make a carbon branch here. So what we did was that first we replaced it with Br, and then that Br we replaced with cyanide group. An important thing to remember is you cannot add water in there because water can split into H and OH, and that OH can also come and replace the Br, basically undermining the whole process. So that's why, because water can't be used, we use ethanol as our solution, and to provide the CN, we provide or we use KCN, NaCN, or HCN. Then we had the process of ammonia, and we saw that ammonia can split, not just ammonia can't just react as a base, which it usually does. It also has another role to play, that it can convert to amine group and H positive group. And in that case, what it does is that its amine group starts and attacks the carbon inside, basically substituting the Cl that we have, and you're able to get amines from ammonia. Now, coming back to this nitrile group over here, this nitrile can actually do two things based on what it is added to. So this nitrile group is used to make buffers, okay, or we can use to make buffers. So what happens is that, for example, I have propane nitrile, the one that we had just over there. So CH3, CH2, CN, and this can react with water in the presence of acid. And what it does is that basically the amine, the nitrogen, it takes the H positive and forms ammonium. So the nitrogen goes away, forms ammonium, and carbon oxidizes and carbon converts to carboxylic acid. So the carbon where the nitrogen was, nitrogen got H, carbon got COOH, and you're able to get this compound here. So you have converted, through an acid, you have converted a cyanide into a carboxylic acid, or a nitrile to a carboxylic acid. Now, in case you don't have H positive available, then water can still play a part. And what water does in that case is that if you add the nitrile to water, then it converts it to CH3, CH2, COOH. So all of that is happening. But depending on what you have, of course, it's also forming ammonia. So the primary reaction is that in presence of water, the nitrile group will break down and form carboxylic acid. But it has to be impure water, because impure water does something else. In case H positive is available, as is the case over here, that H positive is given to the ammonia that forms, and it forms ammonium. But in the case of OH minus that's present over here, if water was alkaline, then that alkali basically takes this H positive away from carboxylic acid, leaving us with COO minus. And that is a very important reaction to remember, because in all the reaction that we've seen, what happens is basically wherever you have COOH, that COOH can either provide H positive and form the COO minus charge, or it can just stay there. And based on what's happening here, ammonia can get the H positive that's available or not.
Sir,
You
I
want
don't
something?
understand this.
Okay, I'll start
What
with it.
is this whole process?
Whenever you add a nitrile to water, so CH3, C double, let's suppose I have this, so CN, and I add it to water, then what's going to happen is that this carbon, the one with nitrogen, is going to convert to COOH, and that nitrogen is going to convert to ammonia. That's what water does. But if you add H positive to it, then which one of these two compounds, the ones on the right, which one of these is going to accept H positive?
The ammonia.
Ammonia. That is why this ammonia converts to ammonium. But if H positive was not available, if you had ammonia and OH negative was available here, then which one of these will provide H positive? Carboxylic acid, right? Ethanoic acid. And that's what happened. This ethanoic acid gives the H positive to OH, making this. So basically what's happening is that these nitriles in water can form carboxylic acid as well as ammonia, a mixture of an acid and a base. But depending on what the solution is, if the solution is alkaline, then the base will react. And if the solution is if the solution is alkaline, the acid will react, and if the solution is acidic, the base will react.
So react with what?
Whatever is available, either H positive is available or OH negative is available.
So I don't understand. Did we add OH negative?
Yeah, you don't react it with pure water.
So but doesn't water ionize to give OH negative in the first place? So why are we adding?
Because we have seen that Ka, or acid constant of water, is really, really low. 1 in 10 power 7 water molecules ionizes in pure water. 1 crore में से 1 molecule ने ionize बनना है. So that's really, really low. But in presence of H positive or OH negative, the process speeds up. And that is why you're getting more H positive or more OH negative. Do you get it? So the primary point to remember here is that these nitriles will react with water, produce carboxylic acid and ammonia, but depending on whether the solution is acidic or alkaline, you will either get either get the ions, like acid will convert to ion and react, or ammonia will take H positive and ammonia will react. One of the two is going to react. And you're not able to get both of them separated, just like that.
So sir, this ammonia will react.
If the solution is alkaline, then the acid part will react. If the solution is acidic, ammonia part will react. इस सबको भी भूल जाओ. There's another easy way to remember. Let's suppose we have the COOH formed ammonia form. ठीक है, ये बन गया. Now, depending on the pH of the solution, one of these is going to react. If the solution has a low pH, if there's H positive available, then this will accept that H positive and form ammonium. So ammonia, being a base, will accept any H positive that is available. But if any OH negative is available, then carboxylate, being an acid, will react with it and form water. So what happens when carboxylic acid forms water? It loses the H positive. So in दोनों में से कोई एक चीज react कर जाएगी. The primary thing to remember here is that with water, nitriles break down, form carboxylic acid and ammonia. ये बात समझ आ गई?
जी sir.
Perfect. So now we've seen that you can replace the halogen in there with a nitrile, or you can replace the halogen in there with amine. And in that case, ammonia breaks down and gives us NH2 that goes and attacks this. Okay. What if I wanted to just remove the halogen that I have? What if I want to go back? What if I know that I can convert any alkene by adding an acid, for example, HCl, and make halogen alkane? I can do that. And the byproduct will obviously be, will there be a byproduct? No, there won't be a byproduct. So is there a way to reverse this? Of course, there is a way to reverse this. If I want to make the halogen alkane convert to something else, for example, if I had CH3CH2Br, okay, and I want to break it down. So what will happen? So this is CH2C, this is the compound. So what happens is that this is the opposite of addition. In addition, the double bond breaks and both the carbons get something. In this process, both the carbons lose something and the double bond forms. Okay, so in addition, double bond breaks, both atoms get something. Now, both atoms lose something and the double bond forms. So that's what's going to happen here. This atom is going to lose bromine, this atom is going to lose hydrogen, and you're going to get HBr. Okay, and yeah.
Process called?
What's this process called?
Yes.
We just eliminated. So this process is called elimination. Now here's the thing, you've seen elimination in O levels, but we called it something else. We called it condensation, in which we took H from one molecule and OH from the other molecule and joined them together, if you remember. Polymerization, condensation, polymerization. Or whenever we wanted to make esters, we did this. The difference in condensation and elimination is really simple. Elimination happens within one molecule. Condensation happens within two molecules. But we'll see some examples of condensation, तो आपको वहां से भी clear हो जाएगा. मैं आपको एक चीज याद कराता हूँ ना. For example, if I had CH3COOH and it reacted with C2H5 OH, then what would happen is that this will lose OH and this will lose H and they will form water. And the rest of it will be CH3COO C2H5 and we have formed an ester, right? This is condensation process because you're removing one thing from one carbon, the other from another carbon, but they're both in the different molecules. And then you join them together. In elimination, you're doing something similar. You're removing something from one carbon, something from the other carbon. But because they're part of the same compound, you're creating the double bond. And that's the difference in elimination, condensation. So elimination mein kya hota hai? You just take the two carbons that are adjacent, obviously the one next to the carbon with the halogen. You remove the halogen, you remove the H, and then you join them through a double bond. And you are basically reversed the process of halogen alkane making from alkene. So every process can be reversed. So yahan par ye process reverse ho gaya. Of course, what we need to do this? We added acid to make this. So we will add alkali to reverse this. So over here, we add a strong alkali, NaOH. We can't add water because yahan pe humne water aqueous mein dala tha. So yahan pe we'll add alkali in ethanol. That is all. So it's exactly opposite. And because these are volatile things, we heat under reflux because we don't want them to go away. So that's what we do over here.
So why do we add an alkali in ethanol?
In ethanol, why are we adding an alkali? Because we want the alkali to basically take this bromine out. खुद ही से वो नहीं जाएगा. This sodium ion is going to create a situation where it's going to accept the bromide. Or the अगर sodium ना भी होना, ये जो OH आता है ना, this OH will accept or pull on this hydrogen that's available over here. और उसकी वजह से hydrogen यहाँ से चले जाएगा in presence of this bromine वगैरह. Okay.
So I don't understand why we have to dissolve it in ethanol and not water.
Because water can provide H positive ion, which can basically undermine the whole process. We don't want H positive. So that's what happens here. You're able to get. So this process, we added acid in water to get halogen alkane. The opposite is we added alkali in ethanol. And this basically the OH minus is going to pull on H from one carbon and the bromine goes away as well, providing us with acid, jo ke wahan se nikal gaya by, and the alkane that we can obviously remove. We will get, if the compound is big enough, we will obviously get many isomers. So for example, let's do a couple of reactions. Examples kar lete hain. Let's say I have this compound and I have bromine here, and we do the necessary thing, NaOH in ethanol and reflux and heat and all that. Okay, so what are the products that I could get? one option is that I will remove bromine from here and hydrogen from here, and that will give me, so one option is that I will get the double bond is on the first and second carbon, and I'm left with this compound. Obviously, the byproduct is HBr. That's one option. Another option is that instead of having this, I could remove this bromine and this hydrogen from the adjacent carbon. So that gives me this, where the double bond is on the second carbon. They're both butene, but one is but1ene and the other is but2ene. Okay. Similarly, we could do something like this. Okay, let's start with this. This is easier. So what is a product that I get? So obviously the conditions are met. NaOH, ethanolic, reflux. Yeah. So what's a product that I could get? Badai, what's a product I could get?
Sir, if we remove both of the BRs, does that mean we'll get two double bonds?
So the thing is, we have to remove both the BR, but ऐसा नहीं होता कि एक BR और दूसरा BR आपस में bond कर जाएंगे. Because remember, they're going away as ions. So bromine as a negative ion and bromine, the other one as a negative ion. Bromides, both of them will not react with each other. They need H positive. So over here, I could get one isomer in which bromine goes from here and hydrogen goes from here. Or in another case, I could get bromine going from here and hydrogen going from here. Similarly, one case is when bromine goes from here and hydrogen goes from here. And another case is bromine goes from here and hydrogen goes from here. So you can get 4 different isomers depending on which happens. Okay? So for example, the simplest case is that I remove, for now I'm removing this bromine and this hydrogen, this bromine and this hydrogen. So if I do that, I will end up with the triple bond here, because HBr दोनों sides से निकल गया. This is one HBr, this is another HBr. So both of them leave us with double bond, not triple bond, sorry. Okay. And I'm able to get this compound. ये पूरा हो गया? नहीं, triple bond ही होगा. Yep. This is a very rare case. एक और option हमारे पास क्या है? That you remove this bromine and this hydrogen and this bromine and this hydrogen. It's the simplest case, and in this case, I will end up with a double bond on the second carbon and a double bond on the fourth carbon as well. In fact, this will be a double bond on the second and first and the third carbon, क्योंकि हमें numbers छोटे रखने होते हैं हमेशा. So this is one simple case that I will get. इसके अलावा और isomers भी बन सकते हैं, but this is the simplest case or the most possible case in my opinion जो हमें मिलेगा. ठीक है? Obviously there are other isomers as well. आप ये bromine ले जाओ और ये hydrogen ले जाओ और ये bromine ले जाओ और ये hydrogen ले जाओ. Or you could remove this bromine and this hydrogen and this bromine and this hydrogen, and that is also another case. So we can get different reactions, different products based on what happens in the elimination reaction. Okay, so we have seen that halogen alkanes, these are all the reactions that they have. Halogen alkanes are versatile, but room temperature pe, we have seen that they don't react as much. We have seen that under heat or under the when they're in high up in the atmosphere, they start to react. And the primary thing that makes them react is the difference or polarity that they have on the carbon and the halogen bond. And because of that, they can do different reactions. Obviously, the most important one is that that bromine or chlorine or whatever the halogen is can be displaced or substituted with other nucleophiles. Those nucleophiles are nitrile, OH, and they can produce different products. They can be amine as well. So you have a whole class of compounds that are made as a result, like the aminoalkanes or aminoalkanes. And then similarly, you are getting acid as a byproduct. वो भी आप वहाँ से निकाल सकते हो. And yeah, so they are pretty versatile when it comes to having the right conditions. एक इनका ये रिएक्शन होगा. दूसरा इनका रिएक्शन हमने देखा elimination, where you remove the Br and the halogen and one hydrogen from the other adjacent carbon. And it has to be that way. It can't be that you remove bromine from the other carbon. Okay. They go out as ions, and those ions need a negative and a positive to make a compound. So that's how the bromine or chlorine can leave, creating HCl or HBr or whatever compound you have as a byproduct, as well as alkene. So you can reverse the process where you make them. And yeah, those are the reactions that we have. So halogen alkanes के reaction हमने देख लिया, उनकी production हमने देख ली. There are 6 processes to produce them and 2 reactions that they have. लेकिन इनमें जो सबसे important चीज है, that is to understand कौन सा halogen alkane ज़्यादा reactive है. So tell me, let's say I have a comparison. I have F, Cl, Br, and I. Okay, so I have fluoromethane, chloromethane, bromomethane, iodomethane. Which one is the most reactive? What do you think?
Say the first one because fluorine and carbon have the most electronegativity difference.
Sure, but doesn't that mean that they'll stick closest, or they're going to stick together the most strongly?
Why?
Because the bond is really strong. Because first one, they're the smallest atoms. They have the highest difference in electronegativity. So the charges are really, really strong, pulling on each other very strongly. The bond length is the smallest because the atoms are small. So bond energy will be high. When the
Sir,
bond energy is high, bond is
because-
stronger, which means it's difficult to break.
Sir, but what if it's like it's a smaller fluorine is a smaller atom, so it's gonna have like weaker intermolecular
Fluorine is
force.
a smaller atom, so it's going to pull on the electrons much strongly. So there's going to be a lot of polarity here. And of course, they're smaller, so bond length भी बहुत छोटी होगी.
Then is it the last one?
Yeah, it is the last one. Because the bond is really weak. Number one, the bond length is really high. Then secondly, the poles are not that strong. So एक दूसरे को इतनी strongly attract नहीं कर रहे हैं. और उनकी bond भी इतनी strongly attract नहीं हो रही है because the iodine atom is really big. So ना bond को वो pull कर रहे हैं, ना वो एक दूसरे को pull कर रहे हैं. So obviously, the bond is going to be much weaker. In fact, if you look at bond energies, this makes sense. This basically explains why the bond energies are the way they are. So this is 485 kilojoules per mole, and this is 340, this is 280, and this is 240. So you can see that there's a declining trend there. And again, the reason is same, that because the atoms are becoming larger, bond length is going to be higher, and the bond strength is going to be weaker. Okay, so that's what we get. Now, of course, what this means is that when they're going to react, iodoalkanes are going to react the fastest, and fluoroalkanes are going to react the slowest. Because वो उसको छोड़ेगा ही नहीं, तो जब वो फ्लोरीन उसको छोड़ेगा नहीं, तो जाके कहीं और क्या react करेगा. Secondly, you know that all the reaction that we've seen, वो किस base पे depend कर रहे थे? They were all based on the idea that you can break the bond between halogen and carbon heterolytically. When we talked about elimination, we said that chlorine as a chloride चले जाएगा और hydrogen as hydrogen ion चले जाएगा. That's heterolytic fission. When we talked about nucleophilic substitution, we said that chlorine as a chloride चले जाएगा और उसकी जगह OH negative आ जाएगा. That's again heterolytic fission. If the bond is very strong, heterolytic fission होने का chance कम हो जाएगा. And that is why fluoroalkanes are almost inert. So fluorocarbons से कोई खतरा नहीं है environment को. Fluorocarbon से है, because chlorine and carbon bond can break down based on the energy of ultraviolet light, क्योंकि उसके पास इतनी energy है कि वो इसको तोड़ देती है. But you see how big the difference is between fluorocarbon and fluorocarbon. The difference is really appreciable. काफी ज़्यादा difference है. मतलब इन दोनों में difference 100 का है, और इन दोनों में difference 145 का है. So this is much stronger than any of these, which is why when आजकल we do not use chloroalkanes for refrigerants or aerosol sprays and all that, because वो जाकर environment को नुकसान पहुंचाते हैं. But we have no problem using fluoroalkanes, because fluoroalkanes environment में जाके कोई भी मसला नहीं करेगा. Of course, another thing that you can relate to this is that how will you differentiate between chloroalkanes, bromoalkane or iodoalkane? How will you differentiate between them? मैं आपसे कहता हूँ ये 3 bottles हैं. One is chloromethane, the other is bromomethane, other is iodomethane. What can you do to those bottles to see कौन सा वाला है? How will you label them? Add a few drops nitric acid, then silver nitrate. What will it do? White precipitate, off-white precipitate, जिसको हम cream भी बोलते हैं, and yellow precipitate. Why? Because silver ion reacts with chloride, bromide, iodide ions to produce these precipitates, insoluble salts. याद है? Please call back soon, or please call back again. Silver was insoluble for halogens, and you can use that idea here. So we can get these precipitates, and using these precipitates हम बड़े आराम से बता सकते हैं कौन सा ज़्यादा reactive है, कौन सा कम reactive. Okay.
What this silver precipitate thing has to do with the halogen alkanes?
Oh, silver precipitate नहीं है, silver compound का precipitate है. So silver bromide is formed, and that is off-white. Silver iodide is formed, and that is yellow. So based on the difference in color, we can easily see which one is more reactive, which one is which compound.
Nahi, like says, so this is how like we identified them.
Just like in O levels, how did you identify between chloride? आपको मैं sodium chloride दे दूँ और sodium iodide दे दूँ. How would you differentiate? Add a few drops of nitric acid so that to destroy any carbonates, and then the silver nitrate, and that will tell us the colors. So it's no different from that. It is technically the same thing.